discuss another new topic on the use of dummy variable that is used to present the effect of qualitative variables. Okay, so in our reflection. So before that, I just want to know next week Tuesday, just one day before Christmas. How many of you celebrate Christmas and do not attend? Not attend the next lecture. Anyone? Sure not. So we really celebrating Christmas. So I'm not sure. I will need to check if I still have the lecture and whether it's allowed or not. If we got that lecture online before, if there's no announcement, meaning that we have physical lecture as usual. Yeah. So next week we're supposed to discuss the distributed light model. So for today, qualitative exponential variable. So meaning that we use our independent variable. So we just use dummy variable to present qualitative variable, or what is called as the effects of different categories. Okay, using dummy variable approach. So dummy variables, sometimes called dichotomous variable, are variables that are created to allow for qualitative effects in a regression model. So the variable is not a real number, it's not the data that we collect, but it is a variable that we create. Okay, dummy variable that we create to present different effects of different categories. The dummy variable will take the value 1 or 0 according to whether or not the condition is present or absent for a particular observation. So if the condition is present, then we assign 1. So we create variable. So just one variable, and not only one variable, but variable that consists of only two values, 1 or 0. So if the condition is present, let's say you want to present the effect of different gender. So we have male and female. So now the condition is whether the observation belong to female, for example, to be considered an example. So we assign 1 if the data belong, the observation belong to female. If we assign 0 if not. Okay. So for example, suppose we are investigating the relationship between savings and income. So our initial model is given here. So our dependent variable saving, and then we have income y to explain the saving. So however, we are concerned that female saving may be below that of male individuals. So let's say we have data, a set of data, and then some of them belong to male, some of them belong to female data, so collected through survey, for example. So there is possible that the way that male and female behave in terms of saving different, so it's not actually the same. So one option we have is just to consider they behave the same. So we have data for male and female, then we can just combine all data. So we do not take into account that observation belong to different genders. So we just consider assume the way that male and female save their money just the same. So we just combine. Again, that one option. So however, we are concerned that female saving may be below that of male individual with income. To test for this, we can introduce a dummy variable to distinguish between the observation for male and female individual in the relation. So another possible way is, if we believe that the way that male and female save their money not the same, different, so we have to include that in model. Okay, so one possible way to by adding or by having dummy variable, that we use dummy variable. We use that variable to present the effect of different gender. Okay. suppose we are estimating 7 equation for male. One method is to restrict our. So another, so there are what we call that just now I mentioned to you that just one way we just make assumption that both male and female behave the same. But if we believe they are not behave the same, they are different, the way that they say they might be different, then one possible way is to split. So split data into two groups. So one data only for male, data for male, and then another group of data for female only, and then we estimate two separate models. That's another one alternative way by estimating model, regression model separately for male and another one for female. However, restricting our sample to a single subpopulation, in this example, male individual does not facilitate comparing different groups. So it does not allow us to perform hybrid testing in order to identify or to say that there is significant difference between the two groups. Although we can estimate the two different models for different groups, but by doing so, it does not allow us to perform hybrid testing in order for us to say whether there is a significant difference between the two groups. Okay, so that's one of the problems. So alternatively, we can just estimate one model, but we include another variable. So what if we wanted to know whether women save the same as men controlling for income? What if we wanted to know whether an additional RM1 in income had the same effect on saving for women as for men? So this one, the first one in terms of intercept, whether we want to know whether the intercept for the two groups the same or not. So this one in terms of the second one, if you can slope whether the slope remain the same for the two groups or not. So suppose we have a sample of individual, we want to know whether women save the same as men contrary for income. So we can create a variable. So we can use different whatever name lah. So we can, for example, D to represent the variable that equals 1 if n individual is female, 0 if n individual is male. So I want to basically for gender we have two groups. We have two categories, two groups, male and female. So we can create up to two dummy variable, one dummy variable for male, one dummy variable for female. But if we have normal intercept beta 0 in the model, then you cannot include, later explain more detail, you cannot include dummy variable for all categories. Otherwise we have a problem of perfect collinearity. So let's say, for example, like this data, we have this one, the seed data, so we have saving as income Y, and then we have variable representing whether it is the observation belongs for female or male. So you need to create a variable. So in this case, let's say you create a variable for female, for example, or male, and you need to assign. So let's say you create a variable. You can use whatever name. Let's say we name it as male. So that we variable male. And then we need, if the condition, we need that if the observation belongs to male, we sum 1, if not, we sum 0. So for example, this one, the first observation belongs to female, then we sum 0. And then the second observation belongs to male, we sum 1. And then and so on. So this one 0, 0, and so on. Okay. And then we can do the same for female as well. So meaning that we have two categories, male and female, so we can create up to 2. But again, if we have a normal set constant, then we can include all in the model. So this one, alternatively, you can use, if you have data in SL like this, you can use function to create that variable. You can use if function. So you can put if. So if this cell equal to F, sorry, this one M, whatever male first, then it is equal to 1, if not equal to 0. So this one way, instead of you assigning one by one, we time consuming. You have large sample size 1000 observation, then you're going to spend a lot of time to assign one by one, either 1 or 0. So you have data. If you have data in Excel like this, then you can use the function. So you put that if that by the value in that column equal to 1, and then you assign 1. If not, you assign 0. So it's 1, 1, 0. So if equal to m, 1. If not equal to m, 0. Okay. So if you drag this down, then you have data variable. So this is what we call data variable. Okay. Dichotomous variable. So either there are only two options, there are only two values, 0 or 1. And at the same time, you also can have data variable for female. So female means that if the observation belongs to female, we assign 1. If not, we assign 0. So this one, male. Okay. So this one, F female, and then we put 1. If not, 0. So in EViews, we are not able to assign values. We are able to ask EViews to simply assign 1 or 0 for categorical variable, if I'm mistaken. So one way to create a variable, you can do that in Excel for example like this. Okay. And then you transfer the data. You transfer the data into the use. So if you want to create a variable for female, and then that is not. So the first observation belongs to female, we assign 1. If not, 0. Okay. So now, as mentioned before, we have a different option. First option, we just ignore the fact that our data belong to different categories, male and female. We just assume all behave the same. So we just estimate model without taking into account male and female. So we just estimate the model and obtain this output. So in the data given here, we have two. Data Lecture9, this one. If this one, the data for all observation. Okay, and then we have D1. So in EViews, you cannot use D. This one is up to you. You can use whatever name you want to for the dummy variable, but you can use D for differencing. D for in EViews for difference. So you cannot. So here I put D1 instead of D, because D cannot be used for other, because it is reserved for differencing. Okay. So just now we have our saving data, income data, and then dummy variable. This one dummy variable for female and not for male. This one dummy variable for female. So we cannot include all. I mentioned just now you cannot. You can create dummy variable for all, but when you estimate model, if you include C constant in the model, then you cannot include dummy variable for all. Okay, later I will explain why. So this one, the first option, we just estimate the model without taking into account that observation belong to different categories. We just assume they behave the same, so we estimate as usual. So they have S space C space Y. So we have these. So this one, if you assume male and female behave the same in terms of the way they save their money, So meaning that in terms of interpretation, we say that for every RM1, for every RM1 of their income, RM1 additional increase in their income, each of them will save about 10 cents. Okay, around 10 cents of that income, every RM1 is saved for. I mean they allocate for saving. Okay. So without taking into account that, meaning that here we just assume that male and female behave the same. Okay. But here, if we believe that male and female behave differently, and then we should just now whether we estimate the model separately or a better way is that we just add a variable. So what happens if we estimate the model separately? So let's say you have to split data into two now. So this one I just sort data, male first and then followed by female. So we have the data given here, data sorted values. So this one, the first 21 observation for male. Let me check. So this one 0. The first 21 observation for male, and the rest for female. Okay. So using the second data set, you can estimate models separately for male and female. So if you do that, you go to quick estimate equation. So you have S space C space Y for male first, observation number 1 to observation number 21. And then you compare, you see the difference. So meaning that we get different estimate. If we estimate the model separately, you can see the estimate are not the same. The same parameter, if for the case for male, this one for male, so 0.06. So meaning for everyone, just now when we estimate models together, it says that and for everyone you get 10 cents goes to saving. But now for if we just estimate for male only, and it says that about 7 cents. So everyone gets 7 cents go for saving. And how about for female? So we estimate another model for female. So we have S space C Y space Y. We have data from 22 to 49. Okay, so just name the first one equation 1. So if we estimate for the case of female only, so we have for every RM1, 14 cents goes to saving, goes to saving. So you see the difference. So meaning that, so that it shows the need for us to consider the fact that different gender behave differently. So we can assume they behave the same in the way, in terms of the way that they save their money. But although here we can get estimate using separate models, the problem is, as I mentioned just now, that we are not able to perform house testing in order to see the significance of the difference between the two groups, male and female. So in order to do that, we have an alternative way. Okay, that is by having dummy variable in the model. So we go back to the earlier data set, not the second one, the first data set. I mean use second set also okay, we also can get the result. Okay, this one, just now I explained to you that is dummy variable, but this one dummy variable for female, not for male. Dummy variable for female. So we can estimate model and add another variable, that is the dummy variable D1. Okay, so we get this one. So how to interpret this one? So, how we are using this model enable us to have estimated model for male and female. So you have to look at this the next slide. So this is our model. So we have dependent variable saving, and then we have a data set, and and then we have dependent, our independent variable, income, and then we add dummy variable, and the dummy variable here represent dummy variable for female. So 1 is equal 1 if the data belongs to female, and then it is 0 if not. If not means that male. Yeah. So you see, for the case of male, D equals 0. Okay, for the case of male, D equals 0. So our model reduced to be this one, beta 0 plus beta 1. Why? Beta this one, because this one is 0 already. Okay. So B1 represent, the beta 0 represent the saving when it comes to the 0. So saving when it comes to 0 for the case of male. And then for the case of female, D equal to 1. Okay, W variable equal to 1. So we have this. So meaning that you can rearrange this one. So your intercept now beta 0 plus beta 2. Beta 0 plus beta 2. So for the case of male, intercept beta 0 only, because this one 0. For the case of female, intercept beta 0 plus beta 2. The slope parameters are the same for both categories, male and female, if you use this model. Okay, but later we consider a model that allows the intercept to be different, that allows the slope to be different as well. So in terms of graphical representation of the model, so this is the model for male. So intercept means that the salary, the saving when income equals 0, the saving for male is given equal to beta 0. Okay, as this one the slope, meaning that for every 1 increase in income, male will save beta 1 out of the 1 ringgit. Okay, beta 1 represent every 1 ringgit how much goes to saving for the case of male. Okay, but for this model consider the slope to be the same for male and female. This model only allows intercept to be different for male, for the two categories. Okay, only the intercept, but the slope we consider to be the same. Okay, so we consider both male and female. For every additional 1 ringgit, the same amount, but only what we call that when y equal to 0, when it comes to 0, so we have to allow them to have different. Okay, so mean that the level of saving to be different. So beta 2 is the difference in the intercept between male and female. So just now is the result we obtained just now. In order to know the value of intercept for female, you have to count, you have to calculate. Okay, estimate for beta 0 plus estimate for beta 2. So beta 2 is given by this. Beta 2 is the coefficient for D. Okay, beta 2 coefficient for D, dummy variable. So we have slope to be the same. Slope for both male and female 0.1, 0, meaning that for every 1 ringgit increase in income, 10 cents goes to saving. But when income equal to 0, saving, the what we call the basic saving. Okay, when income equal to 0, for the case of female, they are saving negative 14 ringgit. So meaning that negative, so negative. So they don't have income, but they have. Sorry, this one for female. This one for male. For female, this one plus this. Okay, you have to have this one for female, this one for male. Okay. So negative means they do not have it, so maybe they have a debt or they own some money to other person. Okay, when the income equal to 0. So this one, so in terms of interpretation, for the case of beta 1, holding other independent variable constant and increase on N1 income increases the Britten saving by about 10 cents. And then for beta 2, holding other independent variable constant, if we take the men and women with the same level of income, female save 1.17 more than male. So because beta 2 represents additional as compared to male, how much more female safe as compared to male. Okay. So if you use the model, if you consider it is correct, of course you have to, before you in actual practice, you have to check for the whole assumption, the autocorrection. This one not really an autocorrection because autocorrection only happen for the case of time series data. So this one is not time series. It is this one cross-sectional. So although the Wilson value is not that it's not the correct representation of the influence of past observation because this is the cross-sectional. So cross-sectional once you change the order, you get different value of Wilson. Okay, so basically the autocorrection problem happen for time series data. Normally it's happen for time series. It's not time series data. This is a cross-sectional. So you have to understand the difference between cross-sectional and time series. Time series data, whether you have annual data, monthly data, quarterly data, and one time series. Okay, this one the data collected at the same time from different sources. So we have 49 different individuals. So we have the information about the saving, information about the income. So this is cross-sectional. So just now we have different set of order. So different set of data. If you change the order, you get different reversal. So for example, if you use the second data set just now, if you estimate using all data, so we get 0.87. But if you use the first observation before we sort the data, they said 0.5, 0.51. But when you change the order, you sort male first and then followed by female. We estimate the order, we get 0.87. So meaning that the reversion is not correct. It's not valid for the case of cross-sectional. Cross-sectional we can change the order. Time series data you cannot change the order because, for example, annual data you cannot put the data. You cannot change the order. You cannot put the first observation to be the second because it is in order. Okay, time series. But this one cross-sectional you can change the order. Once you change the order, you get different reversal. Okay. So again, autocorrection is not really a problem when we have for the case of cross-sectional data. It is a problem for the time series data because the previous observation influence the current observation. So this one again, but again for this one, if they say assuming that this model is ready for us to perform hypothesis testing, then how to perform hypothesis testing? Then you can perform hypothesis as usual. So what t-test could be run to test hypothesis that men and women have the same saving or the income constant. So in this specification, the expected saving for men and women differ only by beta 2. So you need to test. So here we want, after we estimate, we want to know whether there is significant difference between in terms of saving for male and female. So we test this one. Okay, so because if this is not equal to this one is not equal to 0, then there is difference. If it's equal to 0, there is no significant difference. So we have to test whether beta 2 equal to 0 or not equal to 0. Okay. So you have to test this one, test that has beta 2 equal to 0, to test that expected saving are the same for both groups. So the coefficient on the W variable in the regression 1.17, with standard deviation 3 point something. If you calculate the T ratio, you get 0.38. You compare with the value from T table, so it is less than critical value, so do not reject. Or based on the EBS output, just now EBS output it is okay, this one. So this one, the coefficient for beta 2, the beta 2 will present estimate for beta 2. So this one we can just look at the p-value. So p-value 0.69, it is greater than 0.05, so do not reject. Okay. So instead of comparing the critical value to the test statistic critical value from table, you can just conclude based on p-value. So p-value 0.69 greater than 0.05, so greater than significant level, so we do not reject. So conclude that beta 2 just equal to 0. We conclude that the true coefficient beta 2 equal to 0. So meaning that there is no significant difference between saving for male and female. if we use this model lah. So later we will get different result when we allow the intercept to be different as well. Okay. So there is no significant difference in saving behavior between male and female. Alright, so omitting a category. When we have a single dummy variable, we have information for both categories in the model. Thus, having both a dummy variable for male, female, and one for male is redundant. So you should not include lah. You should only include one because only by using one variable we are already able to know whether the observation belongs to female or male. Because if zero let's say now just now the example we use this one variable for female. So if value 1, then we know the observation belongs to female. If 0, then we know it belongs to male. So no need to include both. So no need to include that variable for all categories. Just here we have two categories, just include one. Okay. So as a result, we omit one category whose intercept is the model's intercept. So meaning that we exclude for this given just now they give the example when we estimate model we exclude for male. So we only include the variable for female. So for the case for the example that we considered just now, male is our reference category. Okay. So male when D equal to 0 is our reference category. Reference means that we refer the other category as compared to this one. So as compared to male, female has additional part of the intercept equal to beta 2. So this is our male, our reference category. So we just include the variable for female. Okay. So again, this omitted category is called a reference category. In the dichotomous case, the reference category is simply the category quadrant 0. For just now, the example just now, when for the case quadrant 0 male, so male is our reference category. When we have a series of dummies, you can see that the reference category is also omitted variable. So let's say you have another dummy variable. So let's say this dummy for gender. You have another dummy variable for additional, the highest education level, for example. So you have let's say you have 3 groups. So meaning that, okay, we take another example. Because they want to have 3 groups. Let's say we have another example. Whether they are working in government or private. Okay. Government or private sector. For example, you have 2 groups. So whether all these respondents, whether they are working in the government sector or private, so you have 2 categories. So you can have another variable. So let's say D, so this one D1 and then D2 if they are working in the government sector, for example. Okay, so you create that variable just like what we did just now. So you create that variable if they are working in government, 1 is not 0. Okay, so you can. So for the case we have more than 2 variables. So when both equal to 0, then that is our reference category. Okay, that's the when all D equal to 0, then that is the reference category. So again, when we have a series of dummies, you can see that the reference category is also the omitted variable. So multiple categories, we can use dummy variables to control for something with multiple categories. Okay, so just now I explained to you, I mentioned to you that if we have, let's say, we have a variable representing the highest education level. So let's say I have 3 categories. Let's say primary school, secondary school, tertiary education. So you have three groups, and then you can create that variable as well. But you can, because we have 3 categories, then although we can create 3 dummy variables, but when you estimate model, we just include 2. Okay, just include 2. You can include that variable for all categories. Understand? So you can. We have, for example, we have highest education level for this 49 respondent. So we have 3 categories: primary, secondary, and tertiary university level. So we can create up to 3 dummy variables for each of the category. when we include that in the model, normally we exclude one. Okay, and that one, the one that we excluded, is going to be our reference category. Yeah? Okay. So any categorical variable can be turned into a set type variable because the base group reference category is represented by the intercept. So the intercept represents the intercept for the reference category. If there are n categories, there should be n minus one dummy variable. If there are a lot of categories, it may make sense to group some together. Example, top 10 ranking, 11. So let's say you have many categories, you have 100 categories, then it's not a good practice that you include too many dummy variables because you remember your degree of freedom, sample size minus number of parameters. So you have too many variables, then you have low degree of freedom, which is to make your model, your estimate to be less reliable. Okay, so do not include too many variables, especially if it is representing different categories. So you have many categories, then what you can do is try to regroup. Instead of 100 categories, reduce it to have, for example, 4 or 5 categories only. Yeah. Then create a variable. Alright, so interaction term. So this allows us to have interaction between, dummy and independent variables in order to allow the model to have different, in order to allow different groups to have different slope as well. Okay. So the first example that we consider only allow the intercept to be different. Right now we want the slope to be different as well. So in order to have that, you can introduce interaction between dummy variable and the independent variable. So when the research hypothesis state that the different categories may have different differing responses to other independent variable, we need to use interaction term. For example, gender and income interact with each other, so that the relationship between income and saving is different, stronger or weaker for males than females. To create an interaction term is easy. We just multiply the dummy and the independent variable. So for example, if we have just now, if we have the same variable, one for female, and then if for the case of male, it will be some 0, so we have t dummy variable. So we just add the interaction between dummy variable and the independent variable, so that we have a different slope parameter for the income. Okay. So in this case, if for the case of male, then we have d equal to 0, this one also is 0, then we only have this one. Because this 0, this one 0, we only have this equation, this part equation for the case of male. So intercept for male, beta 0, and then slope for male, beta 1. Slope for the income, the slope parameter. Understand? The slope parameter is the coefficient in front of the independent variable. Okay. Intercept is the when y equal to 0, when all x equal to 0, then what's the value of y? That is our intercept. So for the case of male, when d equal to 0, so this one 0, this one 0, then we only have this one. So intercept beta 0 for male, the slope for male is beta 1. For the case of female, d equal to 1, this 1 equal to 1, so we have beta 2. This one equal to 1, so we have beta 3y. Understand that? This one, if d equal to 1, so we have beta 3y. So for intercept, beta 0 plus beta 2. Beta 0 plus beta 2 is our intercept for female. And then slope is given by beta 1 plus beta 3. Okay, because we have beta 1y, beta 3y. Beta 1y and beta 3y, so we can combine both. We have beta 1 plus beta 3y. Okay, for the slope. So it is given by this one. Okay, by this. You can see if we include interaction term as well, then we allow the two groups to have not only to have different intercept, but to have different slope as well. Okay, slope as well. So in addition to that, we also can have interaction between dummy variables. So interaction between dummy variables is just like subdividing the program. So we have more, we can subdivide the observation into more different to higher number of groups. Okay. So let's say you have dummy variable for gender and then dummy variable for marital status. So we have, so this one for female and this one another variable to represent whether if one if married, if not married, unmarried, zero. Okay. So you can have if you include interaction term, then it allows us to have we subdivide the groups. Not necessarily just I mean, if we include more than variable, we can subdivide. But if we have we include interaction term, then we can allow the different candidates to have different what we call them, to have different intercept. Again. So in this case, the groups that when all the variable equal to 0 is our different candidate. So when D1 equals 0, when D2 equals 0, so we don't have this. So this is the model for male, unmarried, male who is unmarried, so because both equal to 0. So the intercept equal to this one, slope equal to beta 1. So consider, let's say we have two dummy variables for gender and this one for marital status just now. So we have these two categories only without interaction. So the above model implicitly assume that the differential effect of the gender dummy is constant across the two levels of marital status, and the differential effects of the marital status dummy is constant or the same across the two different genders. That is, if beta 2 equal to greater than 0, positive, the mean saving is higher for female than male. This is so whether they are married or unmarried. Likewise, if beta 3 positive, the mean saving is higher for married individual than unmarried individual. This is so whether they are male or female. So this assumption may be untenable. Many female means safe. So it's possible that there is different behavior between female unmarried and female married. So we can, one way to take or to allow that is by having interaction term. Can a married female may save more than a married male. There may be interaction between the two quality variables. The model is as follows. So if we add this, then we can have we can allow the difference between the effects of married for the case of male and female. Because for male, the effects of married just beta 3. Okay, but in the case of female, the effects of married female is beta 3 plus beta 4. So we allow, we allows the married male, married female to have different effects as compared to the married male. Okay. So going back to the previous example, this one, if we allow both intercept and slope to be different, then we use this model. Okay, we have that variable and interaction between dummy and the independent variable. Then we estimate the model. So we go back to our model. Just now, this one is I put this one. So we just use the first observation. Just use the first data set. So this one for which one? Yeah, for this one. Okay, so this one. The first example, we just allow the intercept to be different. So we just add a variable. Now, in order to allow both intercept and slope, again, so the previous example, the first example, we only allow intercept to be different. The slope to be the same, beta 1. This one beta 1, this one beta 1. But second example now, we allow both intercept to be different as well as slope. So the slope for this one, intercept for male, intercept for male, intercept for female. The slope for male, the slope for female. In order to have this, we need to add interaction term between dummy and the income variable. So we have to re-estimate the model, re-estimate and add interaction y and d1. Okay, so now we know model we have saving as the always dependent variable, and then C for the beta 0 constant, B for the intercept. We call that the common intercept, B, C for the beta 0, and then we have the independent variable Y income, and then we have D1 to represent the dummy variable for female. This allows us to have different intercept, and then in order to have different slope, then we add interaction term between income and the dummy variable. Okay, and then just press OK, so you get the estimate. So you see that before this we get insignificant, but now it becomes significant when we include, when we allow the intercept and slope to be different. Now both intercept and slope both are significantly different for the two categories, male and female. Okay. So now to perform our testing, although we have the estimate here, so we need to perform our testing in order to say from the aspect of from the statistical point of view whether we it is safe for us to say there is significant difference or not. Okay. So we have for the case of joint testing, you can perform the test jointly for both the set and slope. Okay, this one you can perform the joint house testing in order to see or to conclude whether the intercept and slope for two categories are the same or not. If they are the same, then beta 2 must be 0, beta 3 also must be 0 now. If beta 2 0, then they have the same intercept. Male and female to have the same intercept. If beta 3 0, then female and male are having the same slope, which is beta 1. So we need to test beta 2 and beta 3. So you can perform the test whether you perform the joint house testing on both coefficient, or you perform the test separately one by one, individual house testing. So you want to perform the joint house testing, you have to test beta 2 equal to beta 3 equal to 0, both equal to 0. Beta 2 0, beta 3 0. Okay. So that can be done by using the walk test that you learned before. Okay, you can use the walk test. If you perform the test manually, then you have to estimate full model and the system model, get SSE, and then calculate. Okay, calculate, get the test statistic compared to the capability from table. So in this case, this test statistic it is greater, so slightly greater than the critical value from table, at table, and then we reject. Reject meaning that when we reject, we can conclude at least one of these not equal to 0, but we don't know whether both equal to 0 or only one of them. Or if even one of them, we don't know which one, we can only conclude at least one of them not equal to 0. So for this manual approach or manual calculation, then I leave it to you to do later. So you need to estimate full model that has all that variable, and then if the variable, if the coefficient equal to, if the number is true, and this one 0, this one is 0, so this is our model, and you have to estimate this model without the variable, and then you get SSE for the model, and then you can calculate. Okay. For the full model just now, SSE is given here 4127. 4127 this one for the full model. So for the case of restricted model, you have to exclude. You have to remove this D1 and interaction, and then you take the SSE, the sum square of residual. Okay. Now if you can perform the test easily using the walk test. You need to test whether the coefficient beta 2 and beta 3 equal to 0, jointly equal to 0 or not. So you just go to view, coefficient statistic, walk test. Just like the question last week, right? So the first part, very easy, very easy question. second part a bit difficult, but the first part I think all are simple like this equation. I haven't marked the answer now. Okay. So this one we need to test the coefficient for beta 2 and beta 3. So coefficient number 3 and 4, right? Based on the order, coefficient number 3 and 4. So coefficient number 3 and 4 equal to 0. So this one you cannot use the F test. You cannot use this pre-value, because this value is test for all slope. Okay, this one is test for all slope, including for this one beta 1 as well. Okay. So last week I think one of the questions asked you to perform the test. You can just take from here. Okay. One of the questions, first part. So for this example, you want to know whether intercept and slope are jointly equal to 0 or not. You can perform it like this, and just okay. So you get the result, test statistic and p-value. So p-value is 0.04, smaller than 0.05. So you reject the analysis, conclude that at least whether intercept or slope are not the same for the two categories, male and female. Whether either one or both are different. And then, because we reject, so we want to know which one, so you can now perform the test individually. You can perform the test individually for beta 2 and beta 3, but this one you can just perform a test based on the t-test. Okay. The t-test you can just look at the result. You can estimate the result for this one. For individual test you can just look at this one, p-value. So for beta 2 p-value 0.0178. This one smaller than 0.05, so you reject. And you conclude, you reject, you conclude that beta 2 not equal to 0. Okay. But this one, if you perform the test, you calculate the ratio, you divide the estimate minus 0 divided by standard error. So you get negative 2.4, you compare to the value from table, but it produces the same result. So reject, conclude there is a difference in the intercept for male and female. And then for the case of slope, you can do the same. So but you test for beta 3. So you calculate the T ratio 2.5. You compare the value from the table 2.02. So this one greater, so you can make the conclusion. Or based on the p value, it is also the same as 0.013, smaller than 0.05, so we reject. Okay, reject, and now this is. Alright, so suggestion for selecting the reference category, you should have ample number of cases. Okay, so reference category. Which one should be used as reference category? Reference category, the one that the category that we do not include, the category that we do not assign dummy variables. Just now, male and female, we just include dummy variable for female, right? We exclude for male. So male our reference category for this. The example that we considered just now. So this is just suggestion. It's not compulsory, but suggestion on how to choose which category should be used. Should be used as your reference category. So meaning that the category that you should not include the dummy variable. Yeah. So you should have an ample number of cases. The model category is often a good choice. So let's say model category means that which category has higher observation. So just now let's say you have 49 observation. Number of male are higher than number of female, and then you use male as your reference category. Yeah. this example whether we have male or female has higher valuation. But that's an example. Okay, that's the what we call one suggestion how to choose. And then if there is some underlying or inequality in the category, select the highest or lowest category. So just now, for example, I give you an example about the highest education level. Let's say primary school, secondary school, tertiary school. So you have three. That's an ordinal. That's already ordinal because the lowest one is the primary school. The middle one, secondary school. The highest one, tertiary education, tertiary. So that's ordinal. It has some kind of ordinality. So in that case, you can select either the lowest one or the highest one as to be your reference category. Whether the primary school to be a secondary or the tertiary level as your reference category. So you have three categories. You only include two dummy variables. You exclude one. So which one exclude? Based on this suggestion, you exclude whether the lowest category or the highest. So let's say you select the lowest one, the primary school. That's you just include a variable for the secondary school and the tertiary education. Okay. Dummy variable trap. If an intercept is included in the model and if a quality variable has m categories, then introduce only m minus 1 dummy variable. So do not include all dummy variable for all categories. Later when we do exercise, then I will show that it's possible to include all categories, but you have to exclude the constant. Okay. So why we have the problem? So for example, gender has only two categories, hence we introduce only one dummy variable for gender. If we not follow this rule, we will fall into what is called the dummy variable trap. So what is dummy variable trap? The situation of perfect collinearity. So if you go back to the, I think second lecture, I provide this summary of regression in. So the earlier notes also explain about linear dependency between independent variables. You cannot have linear dependency. Remember that I explained earlier in the first lecture. We cannot have linear dependence between different columns of the X matrix. Our X matrix, you express your in matrix form. You have X matrix, which is the first column all equal to 1, and then followed by our independent variables. So we cannot have linear dependence between. Otherwise, we have the problem. Otherwise we have the problems of collinearity, multi-collinearity, the one that we discussed earlier, in whether it's perfect or imperfect. If the linear dependence is exact, then that's what we call perfect collinearity. So for the case of dummy variable, imagine that let's say just now we have two categories, male and female. What happens if you include both dummy variable in your model? So the sum of the two dummies, this dummy variable for male plus dummy variable for female, then we have all equal to 1, right? Because this one plus this one, either 1 or 0. So if we take sum of them, then we have a column. We have all equal to 1. So you notice that this one, the sum of all dummy variable is equal to the first column. The first column equal to 1 because why? The first column represent this one for the intercept, right? We have 1 because we have intercept here, we have greater 0. So the first column in our X matrix equal to 1. So you have two dummy variables, let's say D1, D2. You take sum, dummy variable for female, dummy variable for male. You take sum of these two, you get equal to this one. So you have perfect collinearity. Okay. So when we have perfect collinearity, we cannot get estimate. So we cannot get estimate. So there is no the inverse of the X matrix does not exist. So that's why if you want to include dummy variable, you cannot include them for all categories. As if you have this one, if you have greater 0, you cannot include dummy variable for all categories. If you want to include dummy variable for all categories, then you have to take up this one. Okay. If you take up your intercept, if you take up the gamma intercept greater 0, then okay lah, because you don't have this, you don't have the first column. You You don't have the first column. So even though the sum of all dummy equal to 1, then it's not equal to this one. Okay. But the normal practice is that, we keep the intercept. We keep intercept, but we only include the variable, we exclude one category. Okay, we exclude one category. Okay, that's what we call as double threshold. Because the first column equal to the sum of all dummy variables. The sum of that variable for all categories, not all that variable, but the sum of that variable for all categories. Okay. So if you have three different categories, let's say just now you have for education level, for primary school, secondary school, tertiary school. So we exclude one, so that some of them not all equal to one. Okay. Imagine let's say you have another variable, primary school, secondary school, and then tertiary. You have three categories lah education level. So for each of these, for each observation, only one out of three equal one. The other two must be zero, right? Okay, you cannot have highest education level cannot have more than one, either one. Okay, so some of them equal to one, but if you exclude one, then some of them equal to one, but some equal to zero, because you understand? Because let's say because the sum of all variables, three dummy, three that variable. So you have three variable, you exclude one, so that the sum of the two, only two, just take sum of the two, it's not all equal to zero. Not all equal to one, because some of them must be zero lah. Okay. But you need to make sure lah. If you have that kind of data, if you have three categories, but the third categories, there is no observation belong to third categories, then you still have a problem lah. Understand? You create that variable, but your data only belong for the first two categories. The third one, there is no any of them belong to third categories. You still have a problem lah. Okay, even you exclude the third one, because so you have to find a way. Maybe you exclude. In that case, you only have two categories lah actually, because the third one you don't have observation belong to the third category. Okay, so remember that one. So you have normally we exclude one. You have three categories, then you just include two dummy. You have five categories, just include four dummy for four categories. Okay, dummy variable for four categories only exclude one. Okay, now this dummy variable can also be used to perform stability test, the child test that we discussed earlier. But the problem with child test, it only allows us to say whether parameters are stable or not for two different periods. But it does not tell us which one not stable, whether intercept or slope. Remember, the one lecture 2, okay, lecture 3. Child test. So recall that what we discussed earlier, we can use child test to test whether parameters stable or not for two different periods. Okay, so let's say for the given example, if we want to see whether the parameter is the same, still stable means the same. Okay, or not stable, meaning the parameter no longer the same for the period before 1976 and before 1977 and after 1976. Okay, two different periods. So we perform a test using a child test, but we, in terms of the conclusion, we can only conclude after if we reject. If we reject, we can only conclude that the parameters no longer not stable for the two different periods, which suggests that we need to estimate the model separately. Okay, we cannot just use the whole entire data set to estimate the model, because the result suggests that parameters not stable for the two different part of the data. But we do not know which one not stable, because this one, you look at the hypothesis testing, the null hypothesis, whether we are testing whether the intercept as well as slope, intercept and slope the same or not the same. if we reject the null hypothesis, we conclude that at least one of them not the same for the period before and after. But we do not know which one. We do not know whether the set or slope. Okay, we do not know if the set or slope is the one that's not stable or both. The Chow test, we can only say that whether parameters still stable or not, same or not before and after, but we don't know which one. We do not know which one. So as alternative, we can use dummy variable approach. Okay, we can perform the same test. We can obtain the same result, but using the dummy variable approach also allows us to identify. Okay, identify which one is not the same. If it's the set or the slope. If the slope, which one? The slope for x1 or x2 or x3 or x4. Okay, so we open the same data that we used before. Stable test. So recall how we performed the test before. So we estimate the model first. So we estimate model as usual. So we have y space c space x1, x2, x3, x4. So now for the stability test, it's just like we are having two groups, just like male and female. But now this one, the first group is the period before the 1977. And then the second category, the second group is the period after. So it's just like we have two categories. Just like we have two categories. So before and after. Okay. So now, if we just to refresh what we did before, we estimate model and perform the Chow test. You go to view, stability test, the Chow breakpoint. We just put. So some of you asked me through email, so how to decide this one, the breakpoint dates? It is the first point in the second subsample. The first point, second subsample. In our case, second subsample is starting from 1967, right? 1967. After 1976, so the second. So the question says after, or information says after 1976, so starting from 1977. Right. So you have to carefully read this one, the given information. So after 1977, meaning that second period starting from 1977, after 1976. So your breakpoint date starting from 1977. The first point of the second subsample. So we get this result. So what we conclude before? So we get p value 0.01. We reject. We conclude that parameter not stable, meaning that parameter not stable, meaning that whether intercept not the same, or slope not the same before and after, or both not the same. So, but we don't know which one. That's the Chow test. But now we can use dummy variable approach in order to help us to identify. Okay. So what you need to do, you need to estimate a model that allows us to differentiate the intercept and the slope as well. So remember, this is our model. In order to allow intercept to be different before and after, we need to create dummy variable for that period, to period before and after. Okay, now before that we need to create dummy variable before and after 1977. That can be done. You go to quick generic series. Quick generic series. Then you can create dummy variable. Let's say D1 equal. Because we have year annual data, so year greater 1976. 96. So it will create dynamic variable with the sum 1 for the period starting from 1977. Okay, you can see now. So D1 equal kan? So you generate series and then you times this. D1 equal at year greater 1976. Okay, and then just okay. So you have the dynamic variable. You see that the period before all 0 and then starting from 1977 equal to 1. This dynamic variable would have been. So we go back to our model just now. In order to allow the intercept to be different, we need to add the dynamic variable itself. So D1. Okay, but this only allow the intercept to be different before and after the two groups. We need to allow the intercept, the slope to be different as well. So the slope for beta 1, for x1, x2, x3, and x4. So we need to have interaction between dummy and each of the independent variable. So we have x1, d1, space x2 star D1 x3 star D1 sorry, this one is x3 and then x4. So you add D1 and then space interaction x1 star D1, x2 star D1, x3 star D1, x4 star D1. Okay. So now you can perform the same test in order to get the same test, the result, just like the Chow test. How to perform the test equivalent to Chow test? You have to test this one. You have to test the coefficient for the dummy and then coefficient for the interaction. Okay, just like what we discussed just now. So you need to test whether all this equal to 0 or not. Okay, then you should be able to get the same result just like the Chow test. So this one, coefficient number, so 1, 2, 3, 4, 5, 6, 6, 7, 8, 9, 10. 6 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So view, coefficient statistic, walk test, coefficient number 6 to 10. So all equal to 0. Coefficient number 6, 7, 8, 9, 10, all equal to 0. So that represents coefficient the additional part of the intercept as well as additional part of slope coefficient for all independent variable x1, x2, x3, x4. Okay, so you get the same, right? Notice that you get the same result just like the child test. Okay, the test is exactly the same, the value also exactly the same. But if you don't variable for, then you can go to the next step to identify which one is not stable. Okay, but remember that F test and the inverse test is not necessarily the same. It's not always produce the consistent result. Okay, you found the same significant level. You go back to estimate, you can check one by one. So the additional for the intercept, this one for the intercept, remember? The one for the intercept, the additional part of the intercept. Okay, the additional part of the intercept, whether significantly different from 0 or not. So p value greater than 0.05 not significant. So we can say the intercept are just the same before and after. Understand? Intercept just the same before and after. For the case of independent variable, this one, the slope, additional part of the slope for x1, also not significant, right? At 10%. So this one not significant only this one, but this one not significant at 5%, but significant at 10. Okay. If you use 5%, meaning that you get different conclusion, conflicting result between F and the t test. But at least this one almost significant at 5%, not significant at 5%, almost significant. Okay, but so you want to say if let's say based on the child test just now, we say that at least the parameter is not stable, but which one? Based on this result, at least we can say that the slope for the x2 is almost not significant, almost significant at 5%, but at least we know, we get some idea that maybe the most unstable, the most what we call the parameter that's not stable before and after is the coefficient for the slope for beta 2. Sorry, the slope for the x2. Okay, the slope for the x2. Okay. So if from the 10%, then we can say 10%. If 10%, then it is significantly different from 0. But if 5% is not, of course, because just greater is slightly greater than 5%, 0.04. Okay, so I think we take half an hour break. After break, we do the exercise. So we have 6 questions, but only the last 2 on that has data. Let's see if we have extra time, maybe we can discuss the answers for the test as well. Okay, so please be here at 7:50 p.m.
skill.